Okay, for this video, I'll be going through Kinematics Tutorial 2. Okay, figure 1.1 shows a seesaw with two children at its ends, and figure 1.2 shows a velocity time graph of a child for one complete oscillation. Okay, that means the child went up, then came down to its original point. So, what do you need to take note for velocity time graph? Okay, if it's velocity time graph, the gradient represents acceleration. Okay, so do make the distinction between displacement time graph and velocity time graph. And the area under graph represents distance traveled or displacement. Okay, so on top of that, you can also get the velocity information at whichever point in time. Okay, so this is how the graph looks like. They want us to calculate the total distance traveled by the child for the first 2 seconds. Okay, so if you are talking about total distance for VT graph, it is the area under the graph, right? So for the first 2 seconds, so the 2 seconds is here. So this will take the shape of a trapezium. But if you are not used to calculating the area for trapezium, you can actually break it out into two triangles and also a rectangle. Okay, but the answer is this. For the trapezium, it is half the base, which is 3, right? Sorry, the height. In this case, is the height of 3. Add up the two parallel sides. So you should get 4.5 meters. That is the total distance traveled. Okay. Now they want us to calculate the child's average velocity for the first 2 seconds. Now the formula is average velocity equals to total displacement over total time. Okay. So did the child actually go back to its original position? That is the point. Okay. We see that the velocity here is actually positive, right? And if we say up is positive, then down will be negative. So this part is where he is actually going up, right? Where he is going up, because I define positive to be up. Okay, then over here you see that everything below is negative. The velocity is negative. That means over here it is actually moving downwards. So the total displacement is actually 4.5. Okay, as what we have calculated above, and the total time taken is 2 seconds. So this is your answer for B. Now calculate the deceleration of the child from t equals to 1.5 seconds to t equals to 2 seconds. So let's take a look at the graph, because this is testing us on the other concept whereby the gradient represents acceleration, right? So they want us to calculate the deceleration. That means the child is slowing down from t equals to 1.5 to t equals to 2 seconds. So let us take a look. So 1.5 is here. Okay, 1.5 is over here. And 2 seconds is here. So the velocity actually went from 3 to 0, right? So it's easy to calculate. So the acceleration or the deceleration, we use back the same formula, a equals to v minus u over t, and it went from 3 to 0. So v represents final velocity, right? So the final velocity is 0. U is the initial velocity. Okay, so they share the same formula for acceleration and deceleration, but when you get a negative sign for the acceleration, it means that the speed or the velocity is slowing down, is decreasing. And do take note that for deceleration, there is no negative, there's only positive, right? That means we know that the velocity is decreasing. So you should get 6 meters per second square. Okay, so this part is difficult. Sketch the displacement time graph of the child's motion for the first 1.5 seconds. Okay, so very important. Now we need to sketch a DT graph. And what does DT graph, what is important for DT graph? For DT graph, the gradient represents the velocity. Okay, so if we know the velocity from our VT graph, it represents the gradient for the DT graph, right? So this is our DT graph. In our previous tutorial, we actually did from DT to map it into a VT. But now you can map VT to DT, okay? So let's take a look from for the first 1.5 seconds. So for the first 1.5 seconds, okay, we find that the velocity is increasing, right, from 0 to 3. We can also calculate the displacement, right? Calculate the displacement. The displacement, it is half times 3 times 0.5 because it is the area under the graph. So it is 1.5 times 0.5 equals to 0.75 meters. Okay, then we can also calculate for the next time frame, which is 0.5 to 1.5, which is this, which is the area under the graph representing the displacement. So it's the area of a rectangle, so it is 3 multiplied by 1, so it is 3 meters. Okay, but do take note that from 0 to 0.5, the displacement is 0.75. And he continues moving in that direction. So by the end of 1.5 seconds, the total displacement is actually 3 plus previous 0.75 equals to 3.75. So let us just map out this on our DT graph. So we have 0.75 and it is 0.5 seconds after that, right? Then from 0.5 to 1.5, which is 1 second later, the displacement actually went from 0.75 to 3.75, right? Because it actually moved a distance of 3. Okay? Yep. But how do we draw the shape of the graph? You notice that for this part from 0 to 0.75, the gradient is not a straight line. The gradient is not a straight line. It is a curve. Okay? But what kind of curve is it? Is it an increasing curve, gentle to steep, or decreasing gradient curve, steep to gentle? Okay, so over here I will say that it is gentle and here is steep. Therefore, the gradient is increasing. Why is it that it is increasing? Okay, I'm actually analyzing using the answer, but let us see how do we do it. From 0 to 0.5, right, we see that the velocity is increasing. Right, the velocity is increasing at a constant rate. The velocity is increasing at a constant rate, right, because it is a straight line. So if the velocity is increasing at a constant rate, that means the gradient, which represents velocity in the displacement time graph, right? I say again, the gradient of a displacement time graph is velocity, and we know that the velocity was increasing. That is why we need this shape here. Okay? So it's a bit confusing at first, but you need to know the relationship well. Okay, before I comment on this, let us take a look at our VT graph, because that was the answer, yeah? So we see that from 0 to 1.5, right? From 0 to 1.5, the velocity is constant. The velocity is constant. Yes? So, for a displacement time, the gradient represents velocity. And from 0.5 to 1.5, the velocity is constant. Therefore, the gradient is constant. So, we have this shape here. Okay? So, this question is tough, right? Before your WAs, you will need to look at this. Okay? So, you must be able to transfer from DT to VT graph and vice versa. Okay, part E, based on figure 1.2, compare the difference in the child's motion from t equals to 0 seconds to t equals to 2 seconds versus from t 2 seconds to t equals to 4 seconds. So let's look at the graph again. Okay, they say 0 to 2 and then 2 to 4. Basically, you see that it is a mirror image, right? It's just that it is traveling in different direction. Just now we assign the positive to be up, right? So up is positive, and then the negative, it is downwards. Okay, so this is the answer. The child's velocity at t equals to 0 to t equals to 2 seconds is opposite in direction to the velocity, right? Therefore, the displacement is also in the opposite direction. Okay. Now, question 2, it shows the velocity of a toy car changes with time. So again, for VT graph, you need to know that the gradient represents acceleration, and the area under the graph represents distance or displacement. Okay. So calculate the total displacement of the toy car. So at the start, it was having a speed of 6. Okay, and basically to calculate the total displacement, we have to find the area under the graph. And again, there is a positive and a negative component of it. So if I say positive is to the right, then negative will be to the left. And why do we need to do that? Because we are dealing with displacement. Displacement, that's direction. Okay, so let's calculate the positive distance traveled first, or the distance traveled in the positive direction, which is the area under the graph, which is this shape. So if you are not comfortable, not confident again, you may want to break it up into this shape and this shape, so like A, B, or C. Okay, but if you can, you group them into area like a trapezium. Okay, so this is the positive side. Okay, now at this juncture, at time equals to 20, the velocity actually went from positive to become negative. That means it has changed direction. It changed direction. Okay, so maybe it goes to the right, then at t equals to 20 seconds, it moved back. And if this is the start point, and if I want to find the displacement, it will be this amount. Okay, so then I need to find the distance traveled in the negative direction, which is actually this area. Okay, which is a triangle. So if I work it out now, will be half times negative 12 times 5. So I will get negative 30. And this is the value that is being shown over here. So you add them up, the negative will come in, and you will have a total displacement of 165. Okay. Now on axis below, draw the acceleration time graph of the toy car for the first 20 seconds. Okay, so we take note that it's for the first 20 seconds, not that complicated. Let me erase all this. So you see that whenever we give you a velocity time graph, these two concepts will always be tested, right? Which is, firstly, the gradient represents acceleration, and the area under the graph represents the distance. So we have already tested you on this. So now we are going to work on concept 1, which is gradient represents acceleration. We can actually calculate out the gradient for this part A. Let's call this part A, and B and C. Actually, B we don't have to calculate, because the gradient at B is 0. So the acceleration, which is represented by the gradient, is 0. We only need to do for A, and A will be a positive gradient, C will be a negative gradient. So we just calculate the gradient, we should get values like this. And why is it a straight line? Because it is constantly at 1.2 meter per second square for the first 5 seconds. Let's take a look. Okay, you see that this line here is actually a straight line. So it has a constant gradient here. Constant gradient. And if I were to do the calculation, 6 divided by 5 is a constant gradient of 1.2 meter per second square. If it's a constant gradient, that means it has a constant acceleration of 1.2 meter per second square. And that's why I have this value here. Okay, so this one can also be tested. Okay, I think part C is difficult. On figure 2, sketch the velocity time graph of another toy car. That means on the same graph, right? Need to follow instruction. The second toy car starts from rest and accelerates uniformly. Accelerates uniformly means it is constant acceleration. If it's constant acceleration, that means it is having a constant gradient in our VT graph. And what is the value? 2.4 meter per second square for 5 seconds. That means it has double the acceleration. And it started from rest. Okay? So that's why you can work out that it is this part. Okay? So after 5 seconds, it actually reached a speed of 12 meter per second. Okay? Then next part. It then travels with decreasing deceleration. Deceleration means the velocity decreases, and therefore it comes to rest at t equals to 25 seconds. Decreasing deceleration. Okay, so let me draw my VT graph here. Okay, you must be very familiar with VT graph. Now this is a straight line, so this is a constant deceleration. Why is it constant? Because it's a straight line. Okay. Why is it deceleration? Because it has a negative gradient, or the velocity actually decreases. Now we can have other kinds of deceleration. So we go from steep to gentle. Steep to gentle. So this is also deceleration, right? This is also deceleration. I use the red color. But what kind of deceleration? Let's look at the graph. Let's look at the slope. We went from steep to gentler. So it is a decreasing deceleration. Notice the difference between the constant and the decreasing. Then can we have an increasing deceleration? Of course, right? So we can also have something like that. Okay, so if we divide this part, is it deceleration? Yes, because the velocity decreases. It's a negative gradient, right? Over here it is gentle. Over here it is steep. So it went from gentle to steep. So it is increasing deceleration. So this is important. Now that we found our answer to be decreasing deceleration, we can map it to the graph like that. Why is it decreasing deceleration? So if I were to roughly divide this graph into two parts, the curve here is steeper and here becomes gentler. So from steep to gentler, it is decreasing gradient, and it is a decreasing deceleration. So this question is also very popular. Okay. Now question 3. A train from Jurong East was traveling at 45 km per hour when the driver saw a suspicious object on the tracks 35 meters away. The driver's reaction time was 0.4. What is reaction time? That means he will need 0.4 seconds to realize what is that object. So they want us to calculate the thinking distance. Thinking distance refers to the distance traveled before the driver reacts. So take note, the units is 45 km per hour. How do we convert it to meter per second? Because you see other quantities are given in meters and seconds. So we multiply by 1000 divided by 3600. So make sure you know this. And we get a speed of 12.5 meter per second. Okay. Now the thinking distance is the velocity multiplied by the time taken, so it is 5 meters. Okay. Now the driver reacted by applying the brakes to decelerate constantly at 3 meters per second square. So again, make sure that your units tally. So it has to be in meter and seconds. Calculate the time taken. So you can use your A equals to V minus U over T, and you get the value of 4.17 or 4.2 seconds. Okay. Leave your answer in 2 or 3 SF. Now sketch the velocity time graph of the train, including the driver's reaction time. That means we need part A and part B's information. Okay, so initially the velocity was at 12.5 meter per second. So we put it over here. And this is the amount of time that the driver will need to think, right, before he decides whether to step on the brake. So it is 12.5 and then constant speed for 0.4 seconds. Then he decelerated. Now, why do we have this funny value of 4.57? Because this is the time taken for it to decelerate to a stop. But we started the story at time equals to 0. It goes on to his thinking time, and then you need to add this time value to here. So it's 4.57. Okay. And you saw that the thinking distance is 5 meters, right? You can actually calculate this area, and it should give you a value of 5 meters, right? Because the area under the graph of VT graph, it is the distance traveled. Okay, so hence determine whether the train will stop in time to avoid hitting the object. So we have this area, which is 5. We also need this area of the braking distance. So it will be half times 4.17, okay, because the base is actually 4.57 minus 0.4, yeah, multiplied by the speed, okay, which is the height of the triangle. So you get 31.1, and then you decide whether it will brake in time. Okay, now we go to question 4. Car P and Q are moving towards each other along a straight road. They are initially separated by a distance of 875 meters. Figure 4.2 shows a speed time graph. So car P is more complicated. Basically, it accelerated from 0 to 25 within 10 seconds. And then it travels with a constant speed of 25 meter per second. But car C started off with 15 meter per second, and it just carry on like that. Okay, so the area under the graph for car P and Q when they meet must be equal to 875 meters, right? When they meet, because they each travel a certain distance and they must cover 875 meters together. Okay, now determine the time at which the two cars will meet. So this one is actually not really physics lah. It just makes use of some which is the area under the graph. Okay, so let T be the time at which the two cars meet. Okay, how do I know that T is somewhere here? Can it be here? Not possible, because if you were to calculate the distance by the car at this certain point in time, the area under the graph will not be able to be equal to 875. Okay, so it could be somewhere here, here, or here lah, just anywhere. Okay, so let T be the time at which the two cars meet. The combined distance traveled will be the distance traveled by P, like I said earlier. P move a certain distance, Q move a certain distance, and when they meet, they add up to be 875 meters. Okay, so like I said, car Q is the easier one. Okay, because whatever time that we calculate, okay, or whatever time that it takes, we just multiply by the speed of 15. Okay, by the speed of 15. So where is that? It is this part. Whereas for car P, it is actually made of two parts. But luckily, we can calculate this area. We know that for sure they will not meet over here. So we can calculate this, which is half times 10 times 25. So equals to 125 meters. Okay. Then this T, we will need to subtract from this 10 seconds and then multiply by the height, which is the speed, to find the area under the graph, right? So it is this part over here. It's a little bit mathematics, okay, but if you break it down into these three parts, I think you can do it. So the time is actually 25 seconds. Okay, calculate the difference in the speed of car P and car Q at T equals to 40 seconds. At 40 seconds, the difference is just read off 25 and 15, so it is 10 meter per second. Calculate the difference in the velocity. Okay, so velocity, there must be direction, right? because velocity is actually a vector quantity, so there must be direction, and because they are traveling in opposite direction, so you can set going to the left as negative, going to the right as positive. Okay, so both will give you a value of 40 meter per second. Okay, whether you choose left is positive or left is negative. Now, state what is meant by average speed of the car. So this is a definition. It's the total distance divided by the total time taken. Now, explain why the average speed of car P between t equals to 0 to t equals to 10 seconds is smaller than that between t equals to 0 to t equals to 50 seconds. So this part 1 is meant to help you with part 2. Okay. So we are focusing on car P. The average speed of car P between t equals to 0 to t equals to 10. Let's look at the graph here. Okay, so car P is the one that's more complicated, right? So you see that actually from 0 to 10, right, the speed actually went from 0 to 25. Okay, it's not at a constant speed of 25. So therefore, the average will be lesser than from t to 0 to t50. So let's look at the graph again. Okay, see, now they want t0 to t50. We see that a large proportion of the journey he was traveling at 25 meter per second. So definitely the average speed, right, will be average speed from 0 to 50 will be more than the average speed from 0 to 10 seconds, because it's only at 10 seconds that it reaches the speed of 25, but we see that a large proportion of the time from 0 to 50 it was spent with a speed of 25 meter per second. I'm sure you know the logic behind, but maybe you are like me, the English you can't really explain it very well, so let's look at the answer. Okay, so car P accelerated constantly from 0 at t equals to 0 seconds to a maximum speed of 25 meter per second at t equals to 10 seconds. So we quote the data. So the average speed is exactly 12.5 meter per second. But from t equals to 0 to t equals to 50, he spends a large proportion of time traveling at a constant maximum speed of 25 meter per second, right? Therefore, the average speed will be closer to the maximum speed of 25. Okay? So this is your tutorial 2.